Assalamu alaikum, welcome back to EE340. In the previous video, we introduced the concept of wave propagation in lossless media in a free space and in a good conductor. In this video, we'll solve two examples and let's get started. So the first one says like in a lossless dielectric, we're given the intrinsic impedance eta, we're given the permeability, the relative permeability, which is 1, and we're given the electric field, we're given the magnetic field, and we're asked to find the relative permittivity, the angular frequency, and finally the electric field. So let's write what we know about this problem. The first one is, well, lossless. So the conductivity is 0, the attenuation constant is 0, and from this form, the phase constant is 1 radian per meter. The second thing we know is the wave is propagating along the positive z direction. So the electric field, the magnetic field has two components. One is along the negative AX direction, which is this one. The other one is along the positive Y direction. So we should expect the electric field, so the magnetic field can be decomposed into two components. The electric field should be also decomposed into two components. So the first component of the electric field has a direction that follows this formula. Similarly, the second component will follow the exact formula here. So we'll use this fact when we determine the magnitude and the phase of the magnitude and direction of the electric field. But let's start with determining the relative permittivity. So eta is 60 pi. Remember, eta of a free space is 120 pi. And for a lossless media, we have this relation. So we're given that mu relative equals to 1. Therefore, eta is eta naught divided by epsilon r. If we substitute all the values, we will have epsilon square root of epsilon r equals to 120 pi divided by 60 pi, which is 2, which means epsilon relative is 4. Now, to determine the angular frequency, we know that beta is omega divided by c. We got the wave velocity here, since this is not a free space. Therefore, if I expand it, I will get something like this. And this should be equals to 1. Therefore, omega is c divided by square root of 4, which is 2, which is 1.5 times 10 to the power 8 radian per second. So now let's determine the electric field. So let's start with the first component of the electric field. So the first component, E1, is can be written as eta times the magnitude of the magnetic field, the magnitude of H1. So this is the magnitude of the electric field. The direction of the electric field can be determined from this relation. So in order to get a positive z direction here, the electric field must be along the positive y direction. Therefore, E1 is six pi times cosine omega t, which is 1.5 times 10 to the power 8. Let me write it here. Minus z ay. E2, the magnitude of that will be also eta times the magnitude of the second component of the magnetic field, 0.5, which means it's going to be 30 pi. The direction of the electric field should be along the AX direction, the positive AX direction. Therefore, E2 will be 30 pi sine 1.5 times 10 to the power 8t minus c ax for the meters, and the total electric field will be the summation of these two. Therefore, from this exercise we know that it's not necessary that we have one component of the electric field or one component of the magnetic field. We can have two perpendicular components, and we can use what we know about the direction of the electric field. We can use this formula to determine the direction and scale the magnitude of the electric field by the intrinsic impedance of the medium. So the second problem is asking us we are given a uniform plane wave that's propagating in a medium that has a specific electric field. So the medium is characterized by epsilon relative equals to 1, specific permittivity, specific relative permeability, and 3 Simons per meter as a conductivity. So we are asked to find alpha, beta, and h. So before we proceed, we know that the medium is not a free space. Otherwise, sigma should be 0. That's one reason. The other reason is we should not have alpha here. We know also that the medium is not a lossless dielectric. Otherwise, the conductivity should be 0. Therefore, the medium is either lossy dielectric or a good conductor. So let's check the condition of a good conductor. So remember, a conductor is a good conductor if this one is much greater than 1. So 3 divided by omega here is 10 to the power 8, and we have epsilon naught, which is 8.854 times 10 to the power negative 12, and this one is 3393, which is much greater than 1. So the material is a good conductor. So now let's use the equations for a good conductor. So we know alpha is equal to beta, and they are equal to mu omega conductivity divided by 2. If we substitute, we'll end up with alpha equals to 61.4 newtons per meter, beta equals to 61.4 radian per meter. So now let's find the let's find the magnetic field. So we know for a good conductor, the magnitude of eta is the square root of omega mu divided by sigma, which is 800 pi divided by 3. The phase of that is pi over 4. Therefore, finally, let's determine, before actually finding the expression, let's determine the direction of the magnetic field. So the electric field is along the positive AY. The wave is propagating along the positive AC, which means that AH should be along the negative AX. Now, let's find the magnitude of the magnetic field. So the magnitude of the magnetic field will be the magnitude of the electric field, which is 2 divided by eta, the magnitude of eta, which is 800 pi divided by 3, which means that this one is almost 6.69.1 times 10 to the power negative 3. The phase of H is negative pi over 4. Therefore, H is simply 69.1 exponential. Alpha is, we found it to be 61.4, and beta we found it to be 61.4, and the angle is negative pi over 4. The direction is along the AX direction, and the unit is milliampere per meter.